Okay, so it's about time. So are you ready?
Yes, everything is ready on this side. Okay.
Okay, great. So let's get started. Okay, so welcome everybody to this this conference. So this is the modern perspective in birational geometry, and it's basically co-organized by Xuyong Lin and also by Ignition Schindler. Yeah. So we're going to have very intense week of conference. And our first speaker today, we are very happy to have Caucher Birkar. He's now in Tsinghua University, and he's going to talk about the singularities on fibrations. Okay, so thank you, please.
Thank you, Junkai, for the introduction, and thanks the organizers for the invitation. In this talk, the title suggests I'm going to talk about some recent works on singularities on fibrations. First, I will start with some general motivation. And we are going to work over an algebraically closed field of characteristic 0. Now, in general, in algebraic geometry, there is a connection between positivity on one hand and singularities on the other hand. Roughly speaking, the more positivity you have, the more singularities you can create or you could have. And to make this connection more precise and in different settings, establish a connection can be quite challenging. So let's consider some of the very simplest cases of, for example, multiplicity. If we look at a hypersurface X inside a fixed projective space, then the larger the degree of the hypersurface, then the larger are possible multiplicities at points of X. And we can see this very easily if, for example, use this shape here, this in the case of P2, if we have a curve and if the degree is whatever is the degree of X, and then if you take a point, little x on this hypersurface, and then consider a line passing through this point, a general line, then just calculating the intersection number of X with this line, then we can get a bound for how large the multiplicity at this point can be. So the degree of X, which is a global invariant, it measures the positivity of X, and on the other hand, this multiplicity is the local invariant, and it measures singularities. So usually the challenge is to relate this global positivity to this local notion of singularity. In this case, this is of course very simple. You just calculate this intersection number with the line. But we have more subtle invariants of singularities, for example, log discrepancies or log canonical thresholds, and so on. And then relating this type of invariance to positivity can be much more challenging. Another example where positivity and singularities are related is the notion of ramification. For example, if X is a smooth projective curve of genus G, and then you look at the finite morphism from X to P1, then the larger the genus is, the larger the degree of the ramification divisor is, if we use the Riemann-Harris formula. So again, we have a connection here between positivity on one hand and singularities, but in this case, singularities are measured by this ramification. And measuring singularity by ramification is also quite common in number theory. And yet another example is related to degeneration. For example, if X is a smooth projective variety, and if we degenerate X into some other variety Y, then the more positivity X has, usually that you can say that then the more possible singularities you have on Y. So in these examples, there is also one thing we should, here I should mention that we have to be careful. More positivity does not always mean more singularities. It just means more possible singularities. For example, you can have a hypersurface of a very large degree and without any singularity. So it's positivity does not always mean singularity. It just means that what kind of possible singularities you get, like the worst singularities you could get. We are kind of interested in measuring those maximal type of singularities. And it's the same in the setting of the degeneration, because you could have smooth and degenerate into smooth, but you can have smooth degenerate into quite singular variety. Another example is related to the so-called Shafarevich conjecture. In this case, we have C, a smooth projective curve of genus G, and we have a finite closed subset of this curve, let's call it S. And then consider all families from X to C, where X is a surface, and this is a non-isotrivial family, which is smooth over the complement of this closed subset S, and here the general fibers are curves of genus L. So we are fixing here the G and also the L and this closed subset S. And then the Shafarevich conjecture, which was proved, it says that there are only finitely many possibilities for, there is a bounded number of possibilities for all such families. And moreover, you have 2G minus 2 plus the size of S is positive. So you can kind of consider this as, again, a relation between positivity and on one hand and singularity on the other hand. For example, if you want to have more and more families, then you are forced to enlarge your closed subset S. So that somehow kind of put an obstruction on how many families you can construct. Another example is related to linear systems on varieties in general, but here I just state a result on the projective space, although it doesn't really make any difference if you go on more general varieties formulated in a similar way. Both the statement will be quite similar and the proof will be more or less the same. But just for simplicity, I look at the case of projective space. Suppose that we have two real numbers, R and epsilon. Then this result of myself from some years ago, it says that then there is a positive real number T, depending only on these two numbers, R and epsilon, such that if we consider the projective space PD and together with a boundary divisor B, and assume that this is an epsilon low-canonical pair. I hope that all you guys are familiar with these notions of singularities. Epsilon low-canonical is just a measure, it's a way of putting some bound on the singularities. In more precise terms, it means all the log discrepancies are more than or equal to epsilon. And suppose that degree of B is bounded by this number R, and suppose also we have another effective divisor L. These are R divisors or Q divisors. They are not necessarily Weil divisors. And suppose the degree of these two divisors are at most R. Then the statement says that TD together with B plus T times L is half epsilon low-canonical. So what it is saying is that you can actually control, you can put a bound on how bad the singularities can be with respect to both the divisor, boundary divisor P, and also with respect to the divisor L. Now, if you don't have the divisor B here, the proof will actually be quite simple. Now you can just apply a simple induction argument. But when the divisor B, boundary divisor B is involved, here you have to understand the interaction between these two divisors and also the global singularities and positivities. And relating all this data to each other is extremely challenging. So in a way, this is a much more precise version of the first example, where I just talked about multiplicity. But here we are talking about more subtle invariance, and then everything becomes much, much more difficult. And here another example is about Fano varieties. This time let's fix a natural number d and positive real number epsilon. Then the set of all the epsilon low-canonical Fano varieties of dimension d is bounded. As you know, that this is the so-called BAB conjecture. And one of the key components of the proof of this is that we have a minus k, which is an ample divisor, so it is positive, and we need to bound the volume of this minus k, of this ample divisor. And this somehow is related to this local condition on the singularities of being epsilon low-canonical. So again, we have here a connection between global positivity and these local singularities. And this indeed is kind of a key ingredient of the whole proof. And in a way, the previous example is what solves this connection here, what clarifies this connection when we state it for more general varieties, not just the projective space. Okay, so I can sort of, in a general sense, formulate the main problem here. The main problem is, suppose that we have a variety X or a pair XB, and suppose we have a morphism, projective morphism from X to Z. So usually this, we assume projectivity here. Okay, it's difficult to add the word here. F is projective from X to Z. And now what we want to do is to study, to investigate the singularities in this setting. And that means we want to relate the singularities of X, or more precisely of the pair XB, to the singularities of the fibers and the singularities on the base. And we also usually have some kind of positivity around, either is given by the canonical bundle or minus canonical bundle, or some choice of polarization. And we want also to get this positivity involved and then understand singularities in this setting. As stated, this setting is extremely general, and this you can find a lot of problems that can be considered as special cases of this more general problem. I will go through some examples in the course of the seminar. And there are some particular cases that are very important, especially in birational geometry, but actually more generally in algebraic geometry. And that's when X is Fano over Z, or close to being Fano, or more generally when you have a Calabi-Yau structure of XB over Z. Many of the most important problems are actually in this kind of settings, but the problem still makes sense even if you go beyond these cases. Now that I mentioned many times singularities, so let me just remind for the younger maybe students what here we mean by singularities. First, what I mean by a pair XB is that X is a normal variety and B is an effective Q divisor, or more generally R divisor, such that kx plus b is q Cartier or r Cartier. And then, as you know, we define singularities by taking a log resolution, let's say phi from w to x. We write down the pullback of kx plus b as kw plus bw. And then in birational geometry, we define singularities by looking at this divisor bw, this kind of correction term. It just tells you how far your setting is from being smooth or log smooth. Then we say xb is log canonical if the coefficients of bw are at most 1. We say the pair is KLT if the coefficients are strictly less than 1. And we say the pair is epsilon log canonical if the coefficients are at most 1 minus epsilon. So I mention again and again this epsilon log canonical condition, and this is what it means. It means that these coefficients of BW are at most 1 minus epsilon. So that means that there is a gap between these coefficients and the number 1. It's a way of putting some kind of bound on the singularities. So in general, in algebraic geometry, we have many different type of singularities. And depending on what you want to prove or what kind of setting you work on, you may consider different type of singularities. Some statements, they just don't care at all about type of singularities. You can have any arbitrary singularities. For example, the Serre vanishing theorem. It does not depend on what type of singularities you have. But in some other settings, for example, for duality, usually you assume Cohen-Macaulay. And then there are other more traditional kind of singularities, like rational singularities. And in birational geometry, we have these many classes. I define some of them like log canonical, KLT, epsilon log canonical, but also in the older days, people considered a lot canonical singularities and terminal singularities. And in more recent years, now we understand that the right type of singularities for many statements are actually epsilon log canonical. Unless you have a statement which works in general for like KLT or log canonical, but otherwise is quite often the right type of singularities to consider is epsilon log canonical. So this is a kind of analog of terminal or canonical singularities in the old days. I don't talk about much terminal singularity, but instead epsilon log canonical singularities. And this kind of epsilon log canonical singularities, they were initially mostly considered in the for Fano varieties, but it has become clear that they actually play a fundamental role in all cases. It doesn't need to be Fano, general type or whatever. Having epsilon log canonical singularities is usually the right type of singularities to consider. Okay, before I go into the main results and state applications, is there any question?
Any questions? Yes, so far so good.
Okay. Let me recall the so-called canonical bundle formula, which is constructed for Calabi-Yau structures. Suppose that we have a log canonical pair XB and a contraction from X to Z. Contraction just means a projective morphism with connected fibers. And suppose that this pair is Calabi-Yau over Z. In other words, Kx plus B is numerically trivial, which also means Q linearly trivial over Z. So in other words, some multiple of Kx plus B is linear to the pullback of some divisor on Z. And for simplicity, I just look at the case of Q divisors. Then, in the case of elliptic surfaces, with the surface with the elliptic fibration over a curve, the Kodara canonical bundle formula relates the canonical bundle of the surface and the canonical bundle of the curve, and together with some other data coming from singularities and moduli. And this has been generalized to every dimension by work of Kawamata and also Ambro. And the statement is as follows. Kx plus b can be written in a numerical or Q linear sense as the pullback of kz plus bz plus mz, where bz is called the discriminant divisor, and it basically measures singularities on this vibration. On the other hand, mz is called the moduli divisor, and it measures the variation of the fibers. So this is more related to moduli. We can easily define this discriminant divisor for any prime divisor d on z. The coefficient of d in the discriminant divisor is equal to 1 minus t, where t is the largest number such that x b plus t times f upper star d is low-canonical over the generic point of d. In other words, t is the low-canonical threshold of the pullback of d with respect to the pair xb, but we calculate this only over the generic point of d. So obviously, this is a singularity measurement because we are using the low-canonical threshold. For example, if pullback of d, you can maybe just think about, if you're not familiar with this kind of thing, if you think about the case where z is a curve, then the pullback of d, which is pullback of a point, is actually just a fiber. And the more singular that fiber is, for example, the higher its multiplicities are, then the smaller the number t will be, and so the larger the coefficient in the discriminant divisor. So it does really measure singularities. On the other hand, if you have any birational modification of z, let's say z prime, then you can use exactly the same definition to define a discriminant divisor on z prime and also a moduli divisor mz prime, so that if you push down these divisors, then you just get the discriminant and moduli divisors on z. So in other words, you have a compatibility condition here with respect to push down. And then if you put all such discriminant divisors together, you get the so-called discriminant B divisor. B divisor is a kind of divisor on all the birational models of the base, which is Z. And the moduli divisor has some nice positivity properties. Basically, it is a Neff divisor. Let's say in case X and Z are projective, it is a Neff divisor, maybe not on Z itself, but on some modification, on some maybe high resolution, and it has nice pullback properties and so on. But mostly for now, I'm concerned with the discriminant divisor, which measures the singularities. And here is the main result, which says, suppose that d is a natural number and epsilon a positive real or rational number. Then there exists a positive number delta such that if we have the following setting where xb is an epsilon low canonical pair, so for example, a pair with like terminal singularities. But as I said, usually the right thing is to look at this epsilon low canonical. And suppose x to z is a contraction, and we have relatively a Calabi-Yau condition. So it is just like in the setting of the canonical bundle formula, except now I assume epsilon low canonical singularity for the pair. And suppose the relative dimension is d, And also assume minus kx is big over z, or it will actually not really make much of a difference if you consider ample, because if it is not ample, we can make it ample using the minimal model program. So in other words, we are looking at the Calabi-Yau structure here, which is a Fano-type. Fano-type means is close to being Fano. So when minus k is ample over z, this is just then it is Fano. Then the statement says that the discriminant B divisor, this bold B, z on the base has coefficients bounded from above by 1 minus delta. So in other words, these coefficients cannot be very close to 1. And that bounds the singularities on the base. In fact, if we use the language of generalized pairs, this just says that on the base, we have z, bz plus mz. This is usually not a pair in the sense of the traditional definition of pairs, but it's a generalized pair. And this statement says that this generalized pair is actually delta log canonical. You can define singularities for generalized pairs similar to traditional pairs, and then what we have here is a kind of boundedness of singularities on the base. This statement was conjectured by Shakurov around 20 years ago, or maybe before that. There were some known cases of this. The theorem itself is quite recent, just from like 2 months ago, but there were some cases known before. For example, when the relative dimension is 1, this was proved by myself. Another case, fairly general case, was when the fibers, and together with this boundary divisor, they belong to a bounded family. So if you only assume the fibers bounded, this is not enough. You also need to bound the boundary divisor B on the general fibers F. Then in that case, in the same paper, I showed that you can verify this conjecture of Shakurov, but the proof is totally different from the proof of the statement here. But anyway, in particular, if the coefficients of B of the divisor B are not too small, if they are bounded from below by some fixed number, then we can apply the BAB theorem and show that on the fibers we indeed have this boundedness, and therefore the conjecture again holds in this case. So in this kind of nice settings, the statement was already known. But when you go to the full setting, then everything becomes extremely much more complicated, and the proofs have to be totally different from the proofs given before. And now let me state some corollaries which look simpler than the main statement of the this main theorem. The first corollary is that if we fix a natural number d and a positive number epsilon, then again there is positive number delta, such that if x has epsilon log canonical singularities, for example, terminal or canonical, and if x to z is a Fano fibration of relative dimension d, and assume that the canonical divisor of z is Q Cartier, so that we can define singularities, otherwise we cannot talk about singularities, then the base is delta log canonical. So in other words, for Fano fibrations of fixed relative dimension, bounding singularities on the total space implies a bound of singularities on the base. And this was conjectured by McKernan again around 20 years ago. And we can see how this follows from the main statement in a very short argument. Indeed, we have a Fano fibration here, which means minus k is ample over z. So we can easily find an effective boundary divisor B such that xb has epsilon log canonical singularities, and kx plus b is relatively numerically trivial over Z. So you just find B by looking at minus K, basically. And then if you apply theorem 1, the main result, this result says that on the base we have Z, Bz plus Mz. This is a generalized delta law canonical pair. And now if we remove Mz, if we remove Bz plus Mz, both the discriminant divisor and the moduli divisor, then this just simply implies that Z itself has delta law canonical singularities. And again, this was known in some cases. This corollary itself was known in some of the cases. For example, when X is a threefold and Z is a surface, so X to Z is a conic bundle, and X has terminal singularities, then Z has canonical singularities. This was proved by Mori and Prohorov, and the statement itself was conjectured by Iskovsky some time ago, maybe in the 90s. But the proof is quite different. The techniques of Mori and Prohorov is very different from the techniques that I use. Another case of this corollary is when we consider the toric setting, where X is toric, Z is toric, and X to Z is also a toric morphism. Then using combinatorial arguments, Alexiev and Borisov around 10 years ago, they proved this statement. And here is another corollary of the main theorem. Again, suppose we fix D and epsilon, then there is a number L such that if X is epsilon law canonical of dimension D, and X to Z is a Fano fibration over a curve, then the coefficients of all the fibers are universally bounded by this number L. So the number does not depend on the choice of this fibration. It only depends on D and epsilon. Here, for simplicity, I just consider the case when base is a curve, but actually you get the same thing or something similar, even if the base is not a curve. But in that case, you just need to say the relative dimension is fixed, and then say that coefficients of fibers over codimension 1 points are bounded universally by some number. But the case of curves is nicer, makes more sense. So again, this follows quickly from the main theorem, and what we do here, we can find the divisor as before B, so that XB becomes epsilon law canonical, and it has this Calabi-Yau structure over the base Z, and then the coefficients of BZ are bounded from above by some number which is 1 minus delta. So that means that XB plus delta times any fiber is law canonical by definition. This is just the definition of the canonical bundle formula. And by the theorem, by the main theorem 1, and this in particular implies that the coefficients of the fiber F upper star Z, they cannot be more than 1 over delta. So then in this case, L is just calculated. You can just put it to be 1 over delta. Again, there were some known cases of this corollary in the literature when X is a terminal threefold, Z is a curve, and you have a Fano fibration, in other words, a Del Pesto fibration from a threefold over a curve with terminal singularities. This was again proved by Mori and Prohorov. And again, the techniques they use is very different from the techniques used in the main theorem. And here is one more corollary of the main theorem. Again, setting is similar. We have D and epsilon, and we consider X with epsilon low canonical singularities of dimension D is the Fano fibration over a curve. So in this case, here is crucial that I assume the base is a curve. So we have Fano fibration over a curve, and dimension of X is fixed, and singularities are epsilon or canonical, for example, terminal or canonical singularities. Then for every close point Z on the base, there exists a KLT n complement Kx plus B over this point Z. And what does it mean? It means that we can find B an effective divisor such that XB has KLT singularities over some neighborhood of the point Z, and so that n times Kx plus B is linearly. Here is the main point. It's linear, not just numerical or Q linear. It actually is linearly trivial over Z. In other words, this is the pullback of some Cartier divisor on the base. So what this statement is saying, the main point of the statement really is that you have a good understanding of the linear system minus n times Kx relatively over the base. Because of this condition here that I have linearly trivial over Z, that means that this divisor actually will not exactly be itself, but n times B actually belongs to this linear system. So we are claiming here that you can find this number n universally depending only on D and epsilon, so that for any Fano fibration of this type, you can find a very nice member of this linear system minus n times Kx. And these kind of statements are usually very difficult to prove. And another key point here is this KLT condition here. I didn't say low canonical, but I say KLT. In fact, if we consider low canonical, then this statement was already proved in a much more general setting, again by myself some years ago, where the base doesn't need to be a curve. It's in a very general setting. But replacing low canonical with KLT is usually extremely difficult. And this corollary itself was conjectured again by Shakurov a long time ago, but Shakurov conjecture is also, it applies to the case when the base is not a curve, it's a higher dimensional base. But we still need a lot of work to do in order to establish the full version of the conjecture of Shakurov. Indeed, if we consider when the base is not a curve, then we are forced to understand not only these fibrations like Mori fiber spaces, but we are forced to understand a more local setting of singularities, and this is more related to understanding really very local nature of singularities, more related to other problems and conjectures about behavior of singularities, and this still needs a lot of work. And here I also state another result, a kind of not immediate corollary, but more or less corollary of the main result, which is as follows. Suppose we have again D and epsilon, and consider all the projective varieties X such that XB is epsilon low canonical of dimension D for some choice of boundary divisor B. Here we don't need to fix B. And assume that minus Kx plus B is an F, and X is rationally connected. So these kind of structures appear, for example, if you consider limits of even non-rationally connected varieties. For example, if you consider limits of Calabi-Yau, just usual Calabi-Yau varieties, you can end up with this kind of rationally connected Calabi-Yaus, which will be one of the examples of this setting. But here we are only assuming minus kx plus b to be nef, not numerically trivial. So this also includes, for example, Fano varieties. This is in a way it's a case where it includes Fanos and also a lot of things related to Calabi-Yaus and in between. Anyway, the statement that the theorem says that all such X are bounded up to isomorphism in codimension 1. In other words, you can have a sequence of flops, and then after these flops, you get a variety which is actually bounded. And this was conjectured by McKernan and Prokhorov, again, about maybe 20 years ago. In their conjecture, they say that X itself should be bounded. But this is very hard to treat at the moment, just to show that X itself is bounded. But what we can do is that X is bounded up to isomorphism in codimension 1. In other words, up to flops. And that's what people really have been doing in recent years, thinking about these kind of problems. And some previous cases, the dimension 3 case was already understood in a work of myself, Dicerbo, and Svaldi, but also in another work of Chen, Dicerbo, Han, Jiang, and Svaldi, where they prove birational boundedness of X. Here, I can even give you a sketch, at least of partial sketch of the proof. How do we approach such a problem where we only have minus kx plus b is nef? Well, we can take m to be, just define m to be minus kx plus b. And then now you can view x, b plus m. This is not a pair in the traditional sense, but this is a generalized pair, and it has epsilon low-canonical singularities. We could actually even more generally start not with minus kx plus b nef, but just start with an epsilon low-canonical generalized pair. So in other words, we could prove something more general. And it's easy to assume that x is 2 factorial. Now, there are two cases, when b plus m is numerically trivial and when it is not. So for now, suppose that b plus m is not numerically trivial. Then we can use the minimal model program to find, we will have birational transformation from x to some variety y, where y comes with a Fano fibration. In other words, a Mori fiber space onto some variety z. Now, if we transport our data of devices b and m onto y, then we have y, by plus my, which is again a generalized pair, and it has epsilon low-canonical singularities. And ky plus by plus my is trivial, actually just equal to 0. So in particular, is trivial relatively over z. Now, if we apply the main theorem, but the version for generalized pairs, which also holds, then we can conclude that on the base z, we have a similar generalized pair structure using the canonical bundle formula. We get z, bz plus mz, and on the base, we have delta low-canonical singularities for some fixed delta, depending only on d and epsilon. And now, if we use induction and also use the minimal model program, we can actually assume that the base is already bounded. But by induction, what we have is that z is bounded up to isomorphism for dimension 1, but we can modify this Mori fiber space so that z itself becomes bounded. Then we have z a bounded variety and y Fano fibration over this z. And this setting was already studied by myself in another work. Essentially showed that under this kind of setting where you have a base which is bounded and you have a Fano fibration, I proved some quite general boundedness results. And using this, we can show that y belongs to a bounded family. And moreover, if we apply the same results, the same paper, then we can also show that there is a birational modification of y, let's say from some x prime to y, so that x to x prime is an isomorphism in codimension 1. In other words, is a sequence of flops, and so that x prime itself belongs to a bounded family. So here in this story, using generalized pairs is very crucial. Otherwise, we cannot really do almost anything. There is also the other case when b plus m is numerically trivial. And for this, we need a bit different arguments. We actually need to apply the same things, but first we need to, essentially what we need to prove is that that X itself cannot have canonical singularities. It has to be worse because of the rationally connected assumption. And then we can take a modification, appropriate modification of X, and then you get a local labial. And then we need to show that on the local labial, the coefficients cannot be too small in a way. And then we can apply the previous arguments to prove boundedness up to isomorphism in codimension 1 for the modification, and then come back to X and say X has the same kind of properties. So the key ideas is using generalized pairs and then reduction to this final fibration. Okay, so I already stated many corollaries. Is there any question?
Any questions? So in your theorem, so your delta is highly depends on epsilon, and is it possible to determine how they're really related? I mean, for example, if we know epsilon is 1/2, then can we get some estimation of delta?
Yeah, this is a good question, and it's one of the many questions in birational geometry where we prove many statements that some number exists or some family is bounded and so on, but these results almost always are not effective in the sense that we don't actually have a precise number, except if you work in very low dimension, like dimension 2 and sometime for some statement dimension 3, but starting from dimension 4, like very little, almost nothing is known. So this is one of those questions. We know that some number delta exists, but we don't know for the moment what exactly this number should be, except when we work in relative dimension 1. That was done by one of my postdocs, Pingyi Chen. He actually calculated delta in terms of epsilon. But in higher dimension, we don't know. And we cannot know before we prove many other things. For example, this kind of result relies on BAB, and BAB itself is not an effective statement. It is, again, a kind of existence statement. Unless we make that effective first, basically we cannot calculate this delta. But there are good signs that there are good developments that we can, maybe in the not too distant future, maybe we can make many statements effective.
Okay, thank you.
Okay, if there is no other question, I'll try to give you just a little bit. We don't have too much time, almost like 10, 15 minutes. I will just try to give you some ideas of the proof of the main result. So remember, the main result was that we had a pair XB with epsilon low canonical singularities together with a Calabi-Yau structure on some base, and X was a Fano type, or if you like, just assume X is Fano over the base, and we want to control singularities on the base. Now, if we take hyperplane sections of the base or its birational modifications, it's not difficult to reduce the problem to the case when the base is a curve. This was already used in my previous works, and it is not a difficult argument. So the main case is really to understand when the base is simply a curve. And then let's say we pick a close point on this curve, and then t here we calculate is the largest number. I just define t to be the largest number such that xb plus t times the fiber over the point z is half epsilon log canonical. So actually the main theorem says that if you take t to be the log canonical threshold, then we want to bound this t. We want to show that t cannot be very small. However, it's more convenient to work not with the log canonical threshold, but with like half epsilon threshold. Again, we want to find a lower bound for this number t. Now, by standard arguments, there is a divisor t over x, that means on birational models of x, such that the log discrepancy of the pair xb plus t times f alpha star z is reached. It attains this number half epsilon. This is just some simple arguments. And then we are reduced to show that the fiber over this point, fixed point z, has bounded multiplicity along this prime divisor t. So t itself is not necessarily a divisor on x. It's on some maybe very high resolution. We don't exactly know where it is. But still, we can make sense of the fiber over the point z on that maybe high resolution. And then we want to say that that fiber cannot have too large multiplicity along t. So just be careful that we are not working over x itself. This t is somewhere else. Now we can do some simple modifications just to assume that kind of get rid of the fiber in the picture, and just assume that the log discrepancy of xb itself is equal to epsilon along this divisor t. So we, in a way, we can we still need to remember the fiber in order to calculate the multiplicity along the divisor t. So still we want to show that this fiber has bounded multiplicity. Okay, this is just some simple setup. And then what we do next, we use the theory of complements to show that we construct a complement, n complement for some fixed number n. Let's call it kx plus lambda. This is a complement over z. So it basically means the following, that x lambda has log canonical singularities over z n times. Kx plus lambda is linearly trivial over z. As I told you, this is about understanding the linear system minus nk, but the point is that n is fixed. And moreover, we can ensure that this pair x lambda reaches like maximal singularities along this divisor t. In other words, the log discrepancy of t with respect to x lambda we can ensure to be equal to 0. And here we rely on the theory of complements, which was developed by Shakurov and later together with Prokhorov, and its main conjecture was established by myself some years ago. So we are here making crucial use of this theory. Okay, and then next we can use the minimal model program and so on to assume that minus kx is ample over z. In other words, we have a final fibration. And if we take f to be a general fiber, then we can apply the BAB conjecture to show that f is actually bounded. And moreover, therefore, we can maybe replace our number n so that minus nkf is very ample. Then if we shrink the base around the fixed point, then we can assume that minus nkx is very ample over the complement of the fixed point. And then this gives us an embedding of our variety into a relative projective space, but over the complement of the point z. So over the complement, we basically, you could say, we understand almost everything. It's along the special fiber, along that point itself, which is the main problem we have to understand. Outside the point, everything becomes basically clear. So anyway, we have, maybe just look at the picture, the diagram on the right side, we have x to z, and then we can get some y over z, where y lives inside some fixed projective space, fixed relatively over z, because z itself is not a fixed curve. But we have here pq times z. The pq is fixed. And moreover, if we take the birational transform of the support of lambda and call that d, then we have d, a divisor, a reduced divisor on y. And what is the crucial thing here is that yd over z is relatively bounded. We cannot say the same for x over z. X over z is relatively bounded over the complement of the fixed point, but over that fixed point, we have no idea what is going on. But we have this birational model y where relatively everywhere we have boundedness. Okay, but this is still not so good because yd can have very, very bad singularities. It's difficult to control the singularities on yd. And then the next step is to use toroidal geometry to construct a new diagram on top of a new fibration or morphism on top of yd to z. yd to z, we know it is relatively bounded, but we can transform this into a new setting where we have y prime d prime to z prime, and the morphisms from y prime to y and z prime to z, they are generically finite. They are, in other words, alterations, may not be birational. And moreover, the new fibration we get is toroidal. Toroidal means that locally, formally, it just looks like a toric morphism, but only formally at points. So this is a local both on y prime and also z prime. It's not relatively toric, it's just locally look like toric. And moreover, this new toroidal morphism we have is also relatively bounded. And it also has some other nice properties, but not enough time to go into every detail. And then now the idea is to basically try to translate our original problem on X into a problem on this toroidal setting. So what we can do, for example, is we can pull back our divisor, our complement kx plus del lambda to this toroidal setting. And we can see that actually this is kind of controlled by the toroidal divisor d prime. In particular, we can find some divisor t prime on birational models of y prime, which maps onto our given divisor t. And it has similar properties in the sense that log discrepancy with respect to the toroidal pair is equal to 0. We can also obviously pull back kx plus b. This is the initial given pair, and let's call that ky prime by prime. But now there is a serious problem that I struggle with for many years. The problem is that this by prime can have arbitrarily negative coefficients that you just cannot control in terms of the initial data. And so that means that we cannot really work with this pair y prime by prime. And to get around this problem, then what I did is to construct a new pair birational over this toroidal pair y prime. Then we get a new pair w prime bw prime. Its main properties are that it is epsilon log canonical and it has a positivity condition. It is kw prime plus bw prime is nef over y prime. And moreover, the divisor bw prime, if we push it down onto y prime, we can bound the degree of this divisor. So this is just simple. Bounding the degree is not a problem. Construction of the pair itself is also, you just use the minimal model program. This is not a difficult thing. But what is difficult is now is to show that you can bound multiplicities of fibers for such structures, which are just birationally related to our model, which is the toroidal model. And this makes everything extremely complicated because of this kind of discrepancy that we have. If we could just work on y prime itself, everything must have been simpler. But because we are forced to work on a higher model, then this is why the problem becomes so difficult. Anyway, and then what we can do next, so just working here is not enough. We have to still modify our problem. What we try to do is to translate this problem into a problem related to toric geometry. For now, we have only toroidal geometry involved, which is only locally toric. Locally toric is, of course, good for local problems, but for global problems, it tells you almost nothing. What we have is the diagram. As you see here, we have y prime to z prime. This is the toroidal model. And then we can find basically like a toric model, y double prime. And we have a common étale neighborhood of the given. We have a main point y prime on y prime, which is basically the center of our divisor t prime. And then we also get a corresponding point on y double prime. And then we have an common étale neighborhood of the two, which relates local information of y prime and y double prime. But now y double prime is basically, at least relatively, is a toric variety over the base z prime. And then we can translate our problem in the sense that we can construct a new pair w prime, w double prime, b, this should be w double prime over y double prime. So we get a birational structure over this toric variety, and then we also have a corresponding divisor t double prime, which is actually a toric divisor then. And the properties are similar, that we have epsilon low canonical property, we have nefness relatively over y double prime, and so on. So translating the problem itself is not so easy, but anyway, that's not the hardest problem that we face. And we can similarly, because relatively we have a toric structure, we can even just go and work over the relative projective space. So what we have then in the end, we have a pair, let's call it VBV over this relative projective space, and we have a given toric divisor prime divisor over, so in other words, on birational models of this relative projective space. And from the properties of the pair VBV, basically you have epsilon low canonical, and then KV plus BV is nef relatively over this projective space, and we have to bound the multiplicity of the fiber along this toric divisor. The toric divisor itself, we don't know where it is. It could potentially be on a very high model of this projective space. But we can translate this whole thing into a toric problem, although there is a lot of non-toric data involved in the pair VBV, but it is possible to actually translate this into a purely toric problem. But this toric problem actually turned out to be the hardest part of the whole project, and that's why it took me a very long time to figure out. I mean, usually when you, in algebraic geometry, by the time you get to the toric setting, everything kind of becomes easy. Not so difficult, but this time that wasn't the case. But in the end, so there is not time. There is actually a kind of long story about this whole thing. I even used computers for a while to do some calculations, but even computers could not calculate many examples in this toric problem because it involved a lot of computations. Anyway, and then in the end, after 6-7 years, in this year, 2023. So I realized I figured out how to deal with the historic problem, and then it's solved the whole problem. But unfortunately, not enough time to go into any more detail, so I stop here. Thank you.
Thank you very much. Thank you. So any questions?
Yeah, I wanted to ask a question about the last corollary that you mentioned about the birationally boundedness up to isomorphism. Do you expect up to isomorphism in codimension 1? Do you expect it would be possible to remove the isomorphism in codimension 1 to actually obtain boundedness?
Well, at least not with the current technology, because this is related in some way to the Morrison-Kawamata conjecture. And also Totaro has a more generalized version of this, where you have like a Calabi-Yau structure and you want to understand the cone of devices on it, and in some way gives you understanding of all the birationals, in some way birational Calabi-Yau models. But in this case, we don't even have Calabi-Yau, we only have minus kx plus b is nef, which makes things even more complicated. So in the end, yeah, I guess we probably can remove this assumption, but I think at the moment this would be difficult. Even in dimension 3, some of the simplest cases are still not known.
Thanks.
Okay, any other questions? So I'm wondering that what's the next challenge in your mind?
A good question. Yeah, so it's related to this this corollary here. That I said, if we have a Fano vibration over a curve, then we can construct these KLT bounded complements. Now there is a conjecture of Shakurov which says you can do this in general. That means that suppose you have xb or just x. We don't need the b here. We have x to z. This is a Fano vibration, Fano contraction, if you like. This can be birational. So the remaining case is actually the birational case, or even identity. You can just take to be an isomorphism, if you like. And x itself is epsilon log canonical, and the dimension is d. Now, Shakurov conjecture says that then there exists n is fixed depending only on d and epsilon, and there is a KLT n complement. Over any points on the base. So it just means the same thing as in the corollary. It just means that here xb is KLT over some neighborhood of this point, and then n times kx plus b is linearly trivial over this point. If we replace KLT with log canonical, then this is known. This is one of the things I proved some years ago. In full generality, you don't even need epsilon log canonical. But if you want a KLT, so here KLT complement, then this is much harder to achieve. Now there are several cases. If Z is a point, then this means you are working on a global Fano variety, epsilon log canonical, and then in this case, this is basically equivalent to the BAB conjecture. That's when the Z is a point. If Z is a curve, then what we have is this corollary here. But otherwise, if Z is general, if X to Z is in full generality, then you have to understand two things. One of them is related to these fibrations in general and related to the main statement, main theorem. You could, in a way, say that the main theorem here is the relative case, vaguely, is the relative case of this conjecture. But the remaining case is when this is birational. And to understand this birational case, even the identity case, so even if X to Z is just the identity, this is a highly non-trivial, a very difficult problem. And if we understand this birational case also, then we can understand many things about singularities, and you can almost be sure this implies a termination of flips and many interesting phenomena in birational geometry. So I think this conjecture of Shakurov and together with abundance conjecture, I think these two are the top two problems in birational geometry, and definitely among the most important problem in algebraic geometry. Abundance, unfortunately, for now, we don't know almost anything. But this Shakurov conjecture, already the global case, which is the BAB, and the relative case, which is essentially this main result of this paper, it already generates a lot of works and ideas and corollaries. And if we can finish this local case, the birational case also, this conjecture then will imply many other things that as I say. And so that's why I think this conjecture is maybe on more or less the same level as abundance, both in terms of difficulty and also in terms of what it says, what it implies. Abundance in some way is more related to Calabi-Yau structures, but this one is more related to the Fano structures. And both of them give a really very deep understanding of birational geometry and in general algebraic geometry. So I hope that we can do also this case. I don't think this can be done in a few weeks or months, but hopefully in a few years we can also settle this, and then we will be in a good shape.
Okay, yeah, thank you very much. Yeah, we have many young mathematicians here, so maybe they can work on it. Yeah.
Yes, hopefully.
I have a comment to Junkai's question. Possibly the most important thing is to find effective constants, at least in low dimension first, and also bound singularities of the fibers.
Yes.
I think, am I right that this technique allows to bound it at least somehow? Am I right?
Yeah, in lower dimension, of course, we can do more things, but I'm hoping that we can do actually things in every dimension. Now, at least some of the issues we can understand. So, for example, in a recent work with Jihao Liu, this is not published yet, we can essentially find a constant n for existence of complements on triples. We can find an actual explicit number. Even for surfaces, this was proved only, I think, last year. But now for even in dimension 3, we can do this. And I hope that we can, in a few years, to settle this kind of things in every dimension, to be able to calculate like precise numbers, maybe not optimal, but at least to give some number.
Far from being optimal, right?
We have to, one of the things is we have to make BAB effective, and even for some points so far we have to make MMP effective, and that's why things get quite complicated.
Yeah, maybe another question. This result often depends on the dimension of X. Do you think that similar results can also, depending now on the dimension of the minimal BC center of some local Abelian pair on X, so the co-regularity?
Which one? You mean the main result?
The main result, yes.
Yeah, maybe probably one can. In the global case, I think Moraga and some other people they studied this thing that if you look at regularity, then for example, you can construct complements depending not on the dimension but on this like core regularity, and it's just probably maybe the same kind of thing can be done here. Yeah. So for example, if you have if you take this complement and the complement is simple in the sense its topology is simpler, which is related to core regularity, then in fact, yes, that means, for example, if I go to this diagram here, where we go from X to Y to this bounded birational model, then what it could mean is that the center of your divisor, which is T on Y, probably has a certain dimension. Maybe it cannot be too small. And in that case, then it will be easier to apply induction. So the hardest part is, in fact, when this complexity or regularity, in a sense, is maximally complicated. That's when you cannot simply apply induction. And that's where it means that the center of your divisor is just a point, it's not positive dimensional.
Thanks.
Okay, so if there's no more questions, then Caucher again. Yeah, thank you very much for the wonderful talk.
Okay, thank you, and have a good time.
Yeah, have a good time. Yeah.